4th century BCE Greek philosopher Zeno once observed that traveling from one place to another meant having to get halfway there first.
And getting halfway, you have to go halfway to halfway. Ultimately, there are an infinite number of halfways between you and where you want to be.
Ergo, it's impossible to get anywhere.
Practically speaking, such a notion makes no sense whatsoever. Zeno, of course, had no knowledge of quantum mechanics. If he had, he'd have known that, at some point, halfway gets as small as it can.
Our interest in Zeno's paradox does not lie in the notion of space, but of time. We're about to use his halving idea to look at the process of how we got to where we are now from the beginning of everything.
Of course, time may not be constrained by quantum mechanics, so Zeno's paradox could imply that to get to the future, we have to get halfway there first.
Despite the potential for paradox, we begin our halving at a time before time and move forward to the present.
Along the way, we may come to some surprising insights into the nature of time and events. Insights which may expand our thinking and imagining in ways we might not otherwise have ever conceived.
Our universe started roughly 14 billion years ago, not with a whimper, but a bang. According to current scientific thought, there was no 28 billion years ago, twice 14 billion years, since without the existence of things there is no change, and without change, time.
So we start our halving roughly 14 billion years ago, when everything that currently is took the form of a single ultra-dense, ultra-hot, one and only thing, the size of an atomic nucleus.
It's because that one and only one thing instantly underwent dramatic, even explosive change, that time, space, and a seeming infinite number of other lesser things sprang into existence.
But we could not have known this because there would be a large number of halvings, in fact 34 of them, just to get to some 10 months ago, by current reckoning, Wednesday, March 12, 2014, a date when, among innumerable other things, aviation authorities were trying to understand how a missing Malaysian airliner could simply disappear without a trace, and the New York lotto numbers of 9, 11, 14, 16, 49, 57, with a bonus number of 55, were announced to the general lottery playing public.
The halving of 14 billion years ago carries us a long way, some 7 billion years. At that time, the one and only thing had found numerous ingenious ways to specialize into a vast number of other lesser things. Those lesser things, from hydrogen atoms to galactic superclusters, looked and behaved pretty much the way they do today, some 7 billion years later. Among those particulars, however, was not our sun and solar system. The matter out of which our particular system was to form was, at the time, spread out over some 3 light-years of space, 98% of which was made of cold, transparent gases left over from the universe originating Big Bang. The remaining 2% was comprised of the kind of molecular dust and heavy gases making possible later solar system developments, especially that of living organisms. No doubt other suns with their retinues of planets, moons, asteroids, comets, and lesser objects already existed. Those systems came about pretty much the way ours did, being driven into rotary, gravitationally bound action by a blast of high-energy radiation differentially sweeping through primal nebulae. As a result, all that cold dark matter condensed into stars, building up planetary bodies by accumulation out of slowly rotating accretion disks.
By our second halving, the process of creating our solar system was largely complete. Sure, smaller bodies were still crashing into larger ones, but things looked generally as they do today. Meanwhile, on the Eoarchean Earth of 3.5 billion years ago, and probably the Venus and Mars of the time as well, Bacteria, previously quiescent in large rocks floating through space, established themselves wherever conditions made that possible. By 3.5 billion years ago, microscopic living things had already hit the ground running in our solar system, and in particular, our Earth's primordial oceans.
By the time of the third halving, during our planet's Statherian era 1.75 billion years ago, vast changes in Earth's crust were being driven by energy released from its radioactive core. The Earth's continental crust took form, distinguishing themselves from the ocean basins. Earlier, viral mitochondria had formed symbiotic relationships within larger bacteria. Unlike prokaryotic bacteria, such eukaryotic bacteria had internal organelles, like the nucleus, where DNA could be stored, and outside that nucleus, ribosomes, where code embedded in nuclear DNA could be used to make proteins via messenger RNA. The presence of mitochondria ensured that such cells could convert oxygen and simple sugars into energy, increasing metabolic rates many times over. Meanwhile, cyanobacteria were already at work, releasing low levels of oxygen into Earth's largely nitrogenous atmosphere. And eukaryotes were poised to reproduce sexually. This sexy new reproductive approach would later come to support the kind of genetic changes necessary to increase the survivability of living things, while bringing about new opportunities to adapt and adapt to the environment.
By 860 million years ago, in the Tonian era, the Earth's one large supercontinent, Rodinia, began to break up. That supercontinent, like an earlier one brought about by Statherian crustal formation, was incapable of supporting much in the way of life due to a lack of ozone in the atmosphere. But ultraviolet blocking ozone was already on the rise as oceanic cyanobacteria released greater and greater quantities of the oxygen needed to make it up. Meanwhile, single-celled organisms were already reproducing sexually, encouraging them to join together with others in the kinds of colonies that would lead to later tissue-based organisms. Today, advanced fungi can be seen in the form of mushrooms, which display distinct tissue regions. But during the Tonian era, fungi lived as simple colonies like slime molds, mainly along coastal waters.
By the time of our fifth halving, 430 million years ago, the Silurian period, 60% of all marine species were lost to the Earth as the supercontinent Gondwana, mostly comprised of today's southern hemisphere land masses, migrated towards the South Pole, causing a significant chill of Earth's oceans by glaciation. Most species lost were those that came into being and prospered during the warmer preceding Cambrian Explosion. The late Ordovician shift in Earth's climate favored the continued evolution of those vertebrates, mostly fishes, with well-defined jaws, spinal columns, fins, and tails. After dominating the oceans, these true fishes would later go on to colonize the land in the form of amphibians, with wide, squat arms and legs. During the temporal half-step between the Tonian and Silurian, slime molds and other colonial creatures had somehow found a way to evolve tissues, tissues organs, organs systems, and systems bodies. Functions such as ingestion, digestion, motion, and reproduction, once exclusively performed by single cells, had now spread to various specialized organs, mouths, alimentary canals, muscles, gonads, as species diversification went into full swing, then was later derailed by drastic changes in Earth's climate.
By 215 million years ago, a new supercontinent had coalesced as Earth's plates shifted under the relentless heat released by Earth's radioactive core. All this crustal activity drove the remnants of Rodinia together once again.
Earth has an inner sun. That sun radiates energy released by radioactive minerals created by a supernova now more than 5 billion years gone. The energy released by Earth's core is essential to all life on the planet. Early volcanic vents created rudimentary sugars feeding primitive organisms which went on to become all living things. Our Earth's oceans and atmosphere were secreted from an Earth warmed by two suns, one inner and one outer. Earth's inner sun generates a weak but effective magnetic field protecting all Earth's living things from death-dealing blows from our outer sun. Convective cells circulating through Earth's mantle constantly drive the process of continental migration. The last time all the continents were together was some 200 million years ago, a coalescence that started some 100 million years earlier.
By this, our sixth Zenoic halving of time, 215 million years ago, the continents were preparing to drift apart once again. This was the Triassic period, the earliest era of the dinosaurs. A great die-off of older dinosaur forms, the archosaurs, would occur as Pangaea dispersed. The surviving dinosaurs of the later Jurassic and Cretaceous eras would go on to dominate the world for some 140 million years.
As a supercontinent, Pangaea was largely arid and sparsely vegetated. While true plants, rather than simple algae and fungi, may have evolved as early as the Tonian era, 900 million years ago, and diversified in the late Silurian, 420 million years ago, they didn't move inland until the Carboniferous Period, 360 million years ago. These first seed-bearing plants had appeared long before Pangaea came together. Plants, of course, are essential as a food source for animals, which must directly or indirectly consume the carbohydrates, fats, and proteins plants organically synthesize from soil, sunlight, and water. The first animals to move inland with seed and spore-bearing plants were insects. Due to high oxygen levels released by plants and lack of predation, many insects were mega-sized, some 10 to 20 times larger than today. Insects evolved with the plants, moving inland with them during the Carboniferous. Unlike plants, insects fully evolved within their first 100 million years. As a result, most, but not all, of today's insects were around when Pangaea was still a supercontinent, but by the end of the Carboniferous, insects no longer dominated the land.
By the time insects matured as an order, rhinoceros-sized archosaurs populated Pangaea. The dinosaurs of the past, as well as today's birds and reptiles, all evolved from this group of slow-moving creatures. Such creatures were held up by short, thick, widespread legs guided by brains similar to modern reptiles, brainstem, bud, and cerebellum. These ancient dinosaurs moved slowly from one watering hole to the next, grazing on the sparse vegetation of a largely arid land. Of course, these lumbering herbivores were prey to equally large, but far less numerous, slow-moving carnivores whose teeth and digestive systems had not evolved to eat the plants of the time. Today, archosaurs take the form of alligators and crocodiles, but in aquatic rather than terrestrial form. By 215 million years ago, the earliest predecessors of mammals, egg-laying monotremes, burrowed into sandy ground by day and nibbled on nearby vegetation by night. Such nocturnal proto-mammals necessarily developed internally generated body heat and improved visual acuity for cool, low-light nocturnal conditions. By this time, too, the earliest, small but sprightly dinosaurs with more efficient kidneys for improved water retention and more evolved brains had begun evolutionary ascent. Such small dinosaurs were warm-blooded, supporting higher metabolic rates. Meanwhile, their intelligence made them capable of more than simple grazing and ambush predation as a way of life. This was the age of eggs. Fish in water had sacs, while creatures on land, shells. Eggs had to be fertilized. Eggs had to be hidden. Eggs had to be protected. Eggs had to be kept warm. But eggs were very much on the menu. Species able to hatch those eggs and raise hatchlings successfully persisted. Those that did not fell by the wayside, leaving behind stony fossils instead of evolving offspring.
The floating of continents on Earth's viscous mantle led to the breakup of Pangaea. With its splintering, the massive Triassic-Jurassic extinction occurred, involving 3/4 of all species. With that breakup, winds and clouds carried rainfall across geographically smaller but far more vital continents and subcontinents. The Jurassic, harboring the largest herbivores land had ever supported, gave way to the Cretaceous.
By our seventh halving, 110 million years ago, flowering plants freely populated the open spaces left behind by huge 130-foot-long herbivores that had earlier trampled their way through the thick, piney forest of the preceding Jurassic. By this time, herbivores were smaller, but quicker on their feet. Increased socialization made it possible for them to better defend themselves against predators who themselves would gain in size and cunning until a 10-kilometer size comet or asteroid struck the Yucatan Peninsula some 45 million years later. The Cretaceous was a noisy place. Social behavior, encouraged by species-specific calls among creatures, was endemic. Although true placental mammals were rare, marsupials birthed young within protected birth sacs and nursed undeveloped embryos on teats. For marsupials, the egg no longer needed a protective shell. Birds, also well represented in the Cretaceous, did not develop this trick. Instead, they retreated to the trees, building nests and using all that extra body heat to mature embryos quickly. This allowed the birds to displace the often larger flying reptiles, pterosaurs. Ultimately, the birds would carry forward the dinosaur legacy, although in much diminished form. By the time of the Cretaceous, the simple Archosaurian brain had sprouted 2 lateral hemispheres, the diencephalon. This allowed the dinosaurs and birds greater freedom of individual behavior. Meanwhile, the first true placental mammals were about to appear. Such mammals sported a limbic system, the emotive brain, reinforcing emotional bonds between parents and siblings while also supporting the ability to play. Fertile soil in which imagination would later take root. As in the earlier Triassic and Jurassic periods, the Cretaceous was a time in which large creatures were always on the move. The high rate at which plant life was consumed made moving on a necessity. Dung left behind by these creatures, along with new species of pollinating insects, such as bees, would accelerate the pace at which flowering plants brought color and beauty to the open spaces.
But the dinosaurs of the Triassic, Jurassic, and even the Cretaceous were not equipped to appreciate such beauty. Lacking in emotive development, their lives were dominated by the drumbeat of survive, eat, survive, grow, survive, reproduce, survive. But out there, beyond the bounds of Earth, a small chunk of leftover protoplanetary material was also moving on, looking to become part of something greater than itself. After a major disaster such as the Cretaceous-Paleogen CP boundary impact event, it takes about 10 million years for Earth's fauna to recover and flourish. Though individual dinosaurs survived for a time, the dinosaurs as an order of living things died off rapidly. Their large, now much too cold, unroosted eggs failed to pass the test of the Great Chill kill-off that followed. By 55 million years ago, during the Paleocene epoch, Earth's continents were undergoing shifts that would lead to their current configurations. Iceland was separating from Europe. Africa and India had yet to crash into Eurasia. South America would remain long distinct from North. Flowering plants were widespread. placental mammals had fully emerged, allowing them to nurture young and utero well past the embryonic stage of development.